The last dot point we need to address in electromagnetism is about electromagnetic radiation. Now, electromagnetic radiation is a term that's used to describe energy that's being radiated due to the motion of a charge, but we'll have a look at in a little bit more detail at what that means. And the first thing we're going to do is actually link back to electric fields. And you should be able to recall that electric fields surround all charged objects. And if we take that electrically charged object and move it, that means that we're going to see that the electric field is also going to move. So the electric field around the object is obviously going to sort of be attached to that object, using the word attached in inverted commas. That field then is likewise going to move, and it's going to change at the speed of light. So that means that the change is not instantaneous. It means that it's going to take a certain amount of time for that change to sort of be propagated along a field line. So if you start out with a charge that looks like this, and let's say it's a negative charge, the field line representing that situation, if we just look at this one field line out to the right, as that charge moves upwards to a new location, so let's imagine it's now positioned up here, so the field line might look something like this, where this section here represents the region where the change occurred, and that's sort of being propagated out to the right. And takes a certain amount of time for that change to occur depending on the distance that it is away from the charge itself. But rather than look at a field line in that sort of orientation, we're going to look at individual points instead. So imagine we have these points in space that are out in this direction, in the direction of propagation, and at each point the field lines are going to be directed towards the charge. So initially the field lines at each of those points would be directed towards the charge in its original location. At that subsequent later point in time where the charges move upwards, those field lines are now going to be directed up towards the position of the new charge. Likewise, if the charge was to then move back down and go the opposite direction, and so it ends up somewhere below the original position, those field lines are also then going to be pointing down towards the new position of the charge. If the charge was to then oscillate backwards and forwards between those two positions, we'd see an oscillation of those electric field lines as well, pointing up and down at each of those points as we've indicated. However, an important point to note here is that the parallel components of those field lines don't vary much. So the parallel components are the ones that are directed towards the charge itself, and we can represent those in this manner by showing that if we break a field line here up into its components, where this is the parallel component and this is the perpendicular. Now if we take the field as it's represented pointing to the bottom position and break it up into its components, you can see there that the parallel component really hasn't changed all that significantly, but the perpendicular component has. So we're not really going to be concerned with what's happening in the direction of propagation. We're going to be looking at the perpendicular components of those field lines. And in particular here, they change orientation so that they're pointing up at some points, but at other points in time they're pointing down. To make that a little bit more understandable, let's have a look at a Desmos representation to show how the perpendicular components of those field lines change. To start with, we have the charge negative Q represented on the left-hand side of the screen. The line across the screen that you can see is the direction of propagation of the electromagnetic radiation. Now, as that charge oscillates, you can see that it's going to be moving up and down the screen. We can also add in the electric field represented by the green line there, showing the electric field at that point around which the charge is oscillating. Let's also add some points in the direction of propagation where we're going to have a look at the vertical component of the electric field. And you can see as the charge starts to oscillate that we have that varying vertical component of the electric field. You can see each of those points, it's oscillating up and down, and it looks like a wave. So electromagnetic radiation is also sometimes referred to as an electromagnetic wave. Be aware here also that the frequency of the oscillation that we're dealing with is significantly slow, and the movement of the... Be aware here also that the oscillation is significantly slower than what we would usually see for electromagnetic radiation. Likewise, the speed of light has not been accurately represented in this depiction either. Now, to make this depiction just a little bit easier to visualize, I'm going to add in some shaded areas so that we can see more clearly where the electric field is varying over time. So we can see that the perpendicular components of the electric field oscillate backwards and forwards along with the charge. We also need to identify something else about this scenario that's important, and that's the fact that if we have a moving charge, we also then have a magnetic field that is produced. And we saw that earlier in this unit where we looked at current carrying conductors that produced a magnetic field around them. So anytime we have a charge that's moving, it's going to produce a magnetic field. So an oscillating charge, as well as producing an electric field, it's also going to produce a magnetic field. And the points to note about the magnetic field, two things in particular. The first is that it is perpendicular to the electric field. And the second thing that is sort of fairly obvious, but still worth stating, is that it is synchronized with the electric field. So that means it's doing the same thing at the same time. So again, let's have a look at a Desmos representation so you can see that in a little bit more detail. So once again, here we have the varying electric field as the charge oscillates. We're now going to add in the magnetic field. So the axis representing the magnetic field is now horizontal. So this is trying to represent the three-dimensional nature of this scenario. So I've got the direction of propagation to the right, the electric field up and down the screen, and the magnetic field sort of into and out of the screen. So if we then add in the components of the magnetic field, you can see now that the magnetic field is oscillating horizontally, and those shaded regions to represent the horizontal plane in which the magnetic field is oscillating. And we then have the perpendicular components of the electric and magnetic fields oscillating in sync. So they're both doing the same thing at the same time, both reaching a maximum and both reaching a minimum at the same time. So one last thing to mention here about the direction of oscillation. The scenarios that we've been looking at have a fairly clearly defined axis that the charge is oscillating along. In reality, that's not always going to be the case, and the charge will sort of be oscillating in all directions. That means then that the change in the electric and magnetic fields will likewise be in all directions. But for the purposes of what you need to understand for this content, it's enough to identify that the magnetic and electric fields are perpendicular to each other and synchronized. That then leaves us with the definition that we need to record for electromagnetic radiation. And as always, from the glossary, the term electromagnetic radiation can be found in the glossary, and the definition for it is as follows, and we've already described all of the key aspects to it. The first is that it's radiant energy and consists of, as we said, the electric and magnetic fields. And the wording that the definition uses is that they're synchronized and those electric and magnetic fields, the orientation of them is also important. Note here also in the definition it briefly drops in the words electromagnetic wave, and there is also a definition for electromagnetic waves that is somewhat similar to electromagnetic radiation. So the two terms are somewhat interchangeable. It's more just about which phenomena it is that you're interested in, whether you're interested more in energy or whether you're interested more in wave motion. And the last thing here is that it's propagated at the speed of light in a vacuum. Now, electromagnetic radiation covers a spectrum, as shown in this graphic. Now, you'll notice that we start off with the wavelength in meters up the top, and you can see if you follow that scale that it starts off at 10 to the 3, so we're talking sort of kilometers, and then decreases through 10 to the negative 6 in the visible range, through to 10 to the negative 12 for gamma rays. So you can see there's a very large difference in the wavelength as you move from radio waves down through to gamma rays. Down the bottom you can see that we have the frequency measured in hertz, and if you think about the wave equation where V is equal to F lambda, in this case V being the speed of light in a vacuum, if the wavelength is decreasing then the frequency must be increasing, and you can see that there on the two scales. Be aware that representation across the middle is not to scale. There certainly isn't the scale factor change from the left-hand side of the wave represented there through to the right-hand side. It's more just to show that the wavelength is getting smaller as you move to the right. The bands in the electromagnetic spectrum, so radio, microwave, infrared, visible, ultraviolet, X-ray and gamma rays, they're not hard and fast bands. There is a little bit of an overlap between them. But they're indicated there so that you know what the general region is that you're talking about. So for example, radio waves and microwaves typically have uses in communication, mainly because they're low energy and can be used over longer distances, whereas ultraviolet, X-rays and gamma rays have more medical applications and much higher energy. So there's the electromagnetic spectrum. There's not too much that you need to actually be aware of with regards to the electromagnetic spectrum, but just wanted to show it to you to identify that there is quite a range of different applications for electromagnetic radiation.